Alright, time for draftphysics.com, debatephysics.com also. Video presentation. Yeah, just going to talk some about mostly hydrogen, I believe, atoms and such, and just some of the properties in terms of maybe what the sun is doing, blah, blah, blah. Who knows where I'll go? Haven't decided yet. So anyway, as a preface, okay, there hasn't been much comment, which is good because most of the comments are just ragged statements, backed up with no physical evidence, no experiments, no anything to really debate. And that doesn't interest me, frankly. So if somebody can't, again, play my arguments and quote my arguments, quote the sentences anyway, and refute them with some sort of evidence, some sort of something they can point to that's really good evidence, frankly. Well, crappy evidence is okay too, because I'll just point out how it's crappy. But anyway, so the website, I do have the 5-minute videos there in the bottom, and the rest, others, the debate, it was just a waste of time. I should have reacted more aggressively in that debate in terms of saying right from the beginning, I gave you, a couple of days to compose an argument refuting my argument, and all he did was his silly math derivative. He didn't address the lever, he didn't address rolling things, didn't address any of the subjects, frankly. And I should have just said, well, let's not bother, because frankly, that's all I'm interested in. Math derivatives that are just circular, where you tell me one formula is correct, and then you create another formula that's, I'd say it's garbage, and then you say another formula that's garbage. Making those tie together doesn't mean anything to me. And right off the bat, I mean, as soon as you say gravity is 9.8 meters per second, or per second squared, you're already lying, because frankly that's not what Newton observed it to be. That's not how he calculated it. It's not how he looked at it. He didn't need to say per second, and he certainly didn't need to say second squared. So it's just silly, frankly. It just shows that you have an aggressive effort to distort and pervert. It's 9.8 meters per second of velocity per 1 second. The per second means 1 second. It doesn't mean any number of seconds, and it doesn't mean second squared. It's a specific ratio, 9.8 to 1. That's the ratio. That's what you put in the formula. And so you just figure out how many seconds it was, multiply it by 9 times 8, and that'll give you your answer. So anyway, do I really want that's it's a question, just because you can't really do half seconds, because it's sort of cheating, because the same 1, 3, 5, 7, 9 Galilean ratio applies, and so you're really not going to go half your amount of velocity that you're gaining. You don't get half of it in half a second. Just doesn't work that way. You get half of it in the first 1/4 of a second, and then you get the second half in the second 2 3/4 of the second. But anyway, it's all important stuff, and physics just will not talk about any of it, and that's just the depressing part. So anyway, there is a simulation video, the double slit video, and so when I reference those, this is where you can get links to them, and I will do that with other subjects, perhaps like this video when I finally get to it, which I think will be now. So let us begin. All right, so the simple argument I made is that hydrogen atoms are really fetal neutrons. Yeah, they can become neutrons, because you're just talking about a simple idea of an electron and a proton associated with each other. All right, and this just obeys the charge rules that I have explained in the simulation video, but clearly what's basically happens is these two things are exchanging force with each other, and only a red force can push the red thing, and only a green force can push the green thing, and a red force goes through the green thing, and a green force goes through the red thing. So I'm really not going to explain that over and over again. But that's the element of the function. So if you just understand that there's forces acting, pressure acting, and the fact is they do have an attraction to each other, okay. But the problem is, okay, is that they're in a universe that's moving them or jostling them in other directions, from other directions. So even though they have some, even though it's quite obvious that all the red coming this way would be turned to green, and all the green coming this way would be turned to red, and therefore inert to either one of them, meaning they would be attracted, there are other forces that keep moving them away from each other in other directions where that rule's not affecting anything. So I guess I should really learn to get my hands out of the way. So the point is there's a lot of torques in the wrong, moving them in different directions. And the truth is I think these elemental particles actually can move in 3 dimensions at once. They could have forward or reverse motion. They could have a left and a right motion, a left or a right. And they can have an up and a down motion, an up or a down. And so when they do move sideways, it's not like this force tying them together can be affected, but it's obviously going to get weaker the further away they move from each other. And so there's a real disadvantage to any sideways movement. So the idea is that this is hydrogen in the sense that it's loose and distant because there isn't enough compression to force the two things closer to each other. So this force overwhelms the forces going side to side. A little bit of jiggle wouldn't bother it, but big jiggle does. So you can sort of understand that the less force there is, the more the system would have bigger deviations in it. And the higher the density of the system, the higher the density of the pressure, the faster the jiggles get, but the smaller distance they can travel. So things stay closer together under higher pressure would be the simple argument. All right, now the trick is that hydrogen doesn't exist in this form very much. And what it really does, okay, when it's in the atmosphere or doing something, it's in this form. And this is a subtlety of physics that they don't talk about much, is the fact that elements are often found in compound form. That is, it is hydrogen, but there are 2 hydrogen atoms stuck to each other. And you can sort of see that, yes, that does create a very interesting arrangement, where you have very strong forces on the outside of the box and strong repulsion on the inside of the box, you could say. Or I don't know how. Diagonally you have strong repulsion, linearly you have strong attraction. And so this would be the foundation of your helium nucleus, frankly. So, you have something very simple here, okay, and you could see that the more it jiggles to, the bigger it would be, okay, in the sense that the more motion there is, the more distant, the objects can be from each other. All right, making this, what the hell, I did that wrong. Yeah, I say, wow, what the hell did I do? So it's not very big. Yeah, I made the little dots smaller, but anyway, so you get the idea. This would be a big atom. It wouldn't take up a small amount of space, it would take up a large amount of space because they really can't get close to each other because of all the torques in all the wrong directions, all the swings in the wrong direction. And so what it really needs to do is be under high pressure where now we can draw it smaller, where everything would be crushed into a smaller package, and then these attractions get very powerful in the sense that now it's harder to push it open. Okay, when there's lots of force affecting it, the attraction force gets stronger and stronger, and the force trying to jiggle it, the jiggles get smaller and smaller. So you can sort of understand if the jiggles are getting smaller and the strength of the force is getting stronger and stronger between the electron and proton, because there's more, red force going in here getting converted into nothing, and more, green force going in this way getting converted to nothing to the proton. That there's a higher pressure on the outside, a low pressure on the inside. The low pressure gets lower and lower as the high pressure gets higher and higher. Okay, so the higher the density of the force, the little bits that are constantly around something, the smaller and smaller it gets. And the argument is once you've compacted them close to each other, then you create what's called a neutron. So you convert what is never an atom. So the truth is, the hydrogen is never an atom. It's always a nucleus. Okay, and it just doesn't have any free electrons. It doesn't have any. It doesn't have the character of an atom where you have this distinctly positive thing in the center. That is something with twice as many protons as electrons. It's not really built out of that. So it's really the elemental form of a nucleus, and then you just build the rest of the atomic table out of this simple arrangement is the basic idea. And the only difference for the helium nucleus is the fact that you just take this same diagram and you just dimensionalize it. So if I could draw a dimension through here, and you put 2 more protons on it. Okay, so now you have 4 protons, 2 going this way, 2 going this way, and they're both attracted to the elemental electron going the other way. So it is a little tricky to draw it. I think I drew it better on another piece of paper. I probably have that somewhere. So there's probably a better way to show it, where you could get the idea that I guess this way works too. Okay, that you have one electron, and what you're really just saying is that you have 2 protons associated. Should have done those different color. Well, anyway, it doesn't matter. We'll just say the red things are the protons, and the red things are the electrons. And yes, you could arrange it. So, Jesus. Yeah, that's not right again either. All right, so that you still have the repulsion between those things, but they're attracted to each other, and these are all repelling each other. But that's when you have to really do the dimensional thing. There's no way to do it without. You have one bar going this way, then you have the 4 things going this way. The square is going this way around that. The 2 electrons. So you have 2 electrons here and here. And then you have the 4 protons like this, making a square around the 2 electrons. And it becomes very tight in terms of a formation, and then you have to add electrons to that and the outside. The next level where obviously the electrons don't like each other, and so whatever you add electrons, they're looking at something that's, did the color problem again. These would be electrons. Anyway, where they're attracted to the protons, but they can't get too close to the other electrons. So they have to find a position suitable. And those basically are your energy orbitals. Now, nothing's orbiting. So that would be the big big, giant argument here where, again, I would argue physics just took something that could have been very simple and they made it complicated. So by accepting a model where the electrons have circular momentum, and somehow, that makes for easy combinations of molecules. Again, that always threw me as a kid. As soon as they said that, as soon as they did this model of the electron being shared by two atoms, it was sort of game over for me in terms of saying, oh yeah, they've really thought about this, because that just doesn't seem like that would really hold stuff together. Stuff is held together pretty strongly, and you're just arguing, as soon as the electron's over here, why would this be hanging around? It wouldn't hang around because it's seeing the other nucleus and saying, hell, I'm getting the hell out of here. The positive nucleuses would be repelling, so why would the other atom hang around? Just wouldn't. So it just makes so much more sense to say it's literally a shared electron, in the sense that there's two atoms, all right, that have an opposite condition. One of them has the extra electron, one of them's missing it, and it just connects and shares it, and then they become symmetrical again. So they just share to create symmetries and balances between their charges. And just like this hydrogen atom, becomes almost something completely different when they're sharing each other's charges. You can't even really tell whether the atom is this way or the atom's that way. Which way does it really, which way is the atom? So the other part to this is the whole getting into the nuclear stuff of, understanding the sun and what happens inside of it. So you have all of this pressure pushing things, okay, by a force that has its maximum strength here at the surface. You go further in, it gets weaker. You go further out, it gets weaker. You go further in, it gets weaker. But it's still a force, and it's still always a force in this direction. So it's always a force in this direction. And the argument is the matter can't really get rid of that force. It's always generating it because it's always in the gravity, so to speak. It's always in the universe, and there's a differential everywhere between the center and anywhere out here. Any as far away as you go, there's still a differential. And so it's always an arrow in, and it's doing that from both sides. And so that's the argument. And so there's a collection of force, all right, inside. So the density of the force increases as you go further and further into the gravitational body. So the further you get, closer and closer you get to the center, the more and more of these arrows are compressing. They're in less space. A whole bunch of arrows out here is now in this much smaller space. So you can understand the force density is getting higher and higher and higher as you go towards that center. And the two forces are competing with each other, which means they can't really cancel. They really do have to push, and then this one pushes. So you can understand, again, if I had a very loose, random, weak amount of force, you could understand that this side pushes a little more, then this side pushes a little more, and it's like flipping pennies. I could have 5 pennies in a row going this way, and then 5, and I could end up with big shifts in the percentage of the force. And the more permutations I have, the less. If I have 10 people flipping the coins, I'm very rarely going to have a problem where I'll have a high deviation in the total number of heads being headed. So the more density, the less the shift is as a percentage. And so the wobbling goes from this to, this in the center, very high frequency, very fast and short, rather than long, slow wobbles It's very fast and short wobbles. And that's the high pressure that shoves these, these these hydrogen 2s, let's call them that, into what we call neutrons. So that becomes the neutron, which, the physicist will admit that decays into an electron and a proton. A neutron is an electron and a proton. They admit it. They concede the point. So it's kind of given us the whole story right there. Once they concede that point, you have a big part of the story that hydrogen compressed is a neutron. And it's the fact that you're going to now put all of these in a tight environment where they might end up, creating sequences that are just one more added on. Okay, so now you're going to create something even a little more complicated. And you could understand that if you could knock one of these elements out, that you'd have two protons next to each other, or two electrons next to each other. So if you could just knock this piece out of here, you'd have proton on proton, electron on electron, and in a highly dense field of force, that means there's a whole bunch of greens coming this way and green coming this way, and they're all getting converted into the pushing red force and the pushing red force. So it's a very high amount of force pushing against the two red things, the pushing force. So they're going to leave at a very high velocity, and that's what you can gain some energy from, is decompressing atoms. So once the sun compresses them, then you have something you can decompress. You have something you can break. And so if the sun is any hotter than the heat of just the compression alone, it's because it's doing some decompressing. But the more likely truth is it's just like with the Earth. I mean, they say the sun is like 7,000 degrees Celsius, I think that is. And the Earth is like 5,000. Okay. So the sun's not that much hotter in the core, but the truth is the sun isn't as dense as the Earth either. And so these are all important facts. And, the Earth has a crust around the outside. So let's just say you could peel that crust off, the cold part, the solid part, and you could reveal its, tear off the first 30 miles or so. Then you have, and that's not that much considering the thing's 4,000 miles across. You're not peeling off that much. You peel off that hard bit, and all of a sudden it's going to be giving off a lot of photons. So it's not like it can't glow, that it can't be producing, a very bright yellow light, if not white light, and it would behave like a little sun. But it's not hot enough, and it's got way too many heavy atoms to be able to do that. So it doesn't have enough light atoms, to shove on the surface to glow them with its heat. And it's almost places like Jupiter, they're caught in the middle because they do have a core, but the core has a crust, and then that crust has a gigantic atmosphere, so they definitely have an atmosphere they could heat and then make it glow, like a gas in a neon tube. But the heat can't get to the part that needs to be, heated to glow. So there's a barrier of heavy elements. So it's the heavy elements that kind of break the capacity for it to excrete white light or visible light. But it's still excreting the infrared radiation. So it's still a very hot thing compared to the very cold universe. All right, so that might be enough for now. But it is pretty clear to see how, once you have hydrogen 2, all Well, that, yeah, that still has the 2 electrons. Yeah, all you have to do is add the 2 protons to have the helium nucleus. So you're most of the way, it's easy to see the building block nature, that you could take the element. Let me just draw that. Yeah, there's a white piece. Almost white, anyway. It's not the greatest paper. I'm very cheap. So all you get is 1982 computer paper. Anyway, it really is that old. Yeah, actually had a printer that used these little dots. Anyway, it's disgusting getting old. Alright, so let me draw it again. Alright, so you have the 2 hydrogen atoms, H2. Okay, Jesus, I did that wrong again. I'm tired and old. Anyway, so let's say the green things are the electrons, the red things are the protons. That would make more sense, of course. And what you're really saying is you just take a proton here and here, through here. So they're going through it. So that you have a proton here, a proton down here. And then the 2 electrons. And that works, in terms of that they would all want to connect. So now you're basically looking down at it, right? So if you're looking down at it, there's an electron, there's another electron straight down below that one, and then you just have your 4 protons in between that sandwich. All right, so you have an electron below this electron, okay, and 4 protons, and that becomes your helium nucleus. And then you can understand, just looking at it, that yes, there would be places out here where electrons could be quite comfortable. And then you have to start talking about their motion. So when they switch locations, that's when they move, okay, and that's what they call the quantum jump. But they're not switching up and down, they're just switching side to side. They could switch up and down. Now, don't get me wrong. Once you have a few electrons rowed here, well, it wouldn't be rowed there, it'd be here, right? Electrons have to be balanced. Yeah, then certainly you could have one jump here, or you can have just one jump sideways. So there's lots of different jumps you can make, and those are the spectral lines. Have to do with what are the possible places it can jump from one location to another if it's given enough momentum, where it would skip from one side of the atom to the other side. But yes, I'm not ready to get into all of that. The other problem with getting into that is, you look at the hydrogen spectrum and it looks way too complicated, right? I mean, it's got more than one line. It's got like 6 lines or something. And you're saying, well, how can hydrogen do that? And then my brain says, well, how can I see the spectral lines for hydrogen? Because, frankly, I can't just stimulate it. I have to burn it to see the spectral lines, right? You can't just heat it. You have to kind of burn it or oxidize it. And so it's combining with another atom. So you're really not seeing the spectrum of hydrogen, because you can't really make hydrogen glow. Now, I don't know about with lasers. I think they use hydrogen and some other gas for one of the lasers. But anyway, I have to see if that makes a difference. You just, whether or not you're taking these hydrogen 2 and you're making it bigger or making it smaller, and that might be possible in stages, but I don't think so. So, but whatever. I have to give that subject more thought. Yeah. And but very busy here actually. Lots to think about. Lots of subjects in physics, and frankly, the physicists have got them all wrong. I mean, just about every single one. Every time they had a simple decision to make, they made the wrong choice. So, I mean, you got this stupid orbiting electron atom, wrong choice. You got wave particle, wrong choice. You got 3-dimensional fixed dimensional universe, versus mushiverse, wrong choice. And then the energy thing, the momentum that worked so well, and they had to screw even that up. They couldn't leave that alone. They had to turn that into wooey nonsense. But it's like every single time. Simple choices. I say obviously you can see the side that should win, push versus pull. There's just no doubt about which one should win, and they chose the one that shouldn't win. And I can't really explain that because I can't think that they're all just lying doopy scum. But, you see their overreaction to the accusation they've chosen badly is to just attack you because you're daring to say they made a mistake, and they just can't even accept that. So you see, they are so fanatic. So maybe it's just the fact that they've been taught wrong, so they teach wrong. And they just can't step out of that bad habit. Just like religious kooks. Mommy said so, and they can't ever grow up. Because it's hard to figure. I mean, it's almost like you wish you could go back a couple hundred years and just make all the arguments that nobody made. Because back then they were open-minded enough to say, yeah, maybe that's a better explanation. They weren't habitized into the nonsense. I guess you would go back to the days when in Rome, when people would debate religion and just saw how weak the argument was. I say so, or my uncle says, some kind of, real fish story. And you'd say, yeah, well, maybe we should listen to that, guy called Darwin. Anyway, till the next time and such and so forth. And yeah, I'm really not interested in comments, frankly, unless you can link to something. And the only thing I'm really interested in is somebody, again, quoting my argument if they're going to comment. Or I'd prefer they make a video and draw something. Explain why they believe what they believe. I've drawn it and explained why I believe what I believe. And the only thing that's going to impress me is a counter argument that contains drawings and citation to physical evidence. The rest of it is just a waste of time, frankly.